right, so this video, what we're going to work on is how to look at data and figure out what the exponents are going to be. Is it zero, first, or second order? So what I want you to write on the top is rate, law, exponents. Okay, so how do we determine it is by looking at what we call data. Okay, so how do we know if it's a zero, first, or second order reaction? We have to look at some data. So what I'd like you to do, if you haven't printed this off, pause the video and print off this data set. And if it makes it more comfortable, you might want to make it a table, okay? Over here, what I've written is experiment 1, experiment 2, and experiment 3. And what we have is a series of some data for us to take a look at. So what I have is 2A plus B as a diatomic goes to 2AB. So I have A, different concentrations of A, different concentrations of B, and this is my rate, molarity over seconds. Okay. So what I have is I did an experiment, experiment 1. Okay, this is my concentration of A, this is my concentration of B. These reacted to make product, and I had a way to measure the rate. Okay, and I got 3 molarity per second. I threw it down the sink, and I did a second experiment. Okay, I put 2 molarity of A in there, 1 molarity of B, and 3 molarity per second was the rate when I measured it. Okay, experiment 3, same. Okay, so for these reactions, what I'm going to have you do is 3 different things. Okay, first is to write out the general rate law, and this is usually pretty much the same. You're going to write rate on the left and put an equal sign, and then put a lowercase k, and then you're going to take the reactants. Okay, we are not going to look at the stoichiometry, so it does not matter that there's a 2 in front of that A there. Okay, all I'm going to do is put A in brackets, and they need to be in brackets. They can't be in parentheses. Okay, and I am going to put the letter M on top. Okay, then I'm going to put the second reactant, B, as a diatomic, and I am going to put it as the letter N. Okay, so this is your general rate law. Okay, the next letter you would use if you had a third is going to be the letter P. Okay, you do not use the letter O because that looks like a zero order reaction. All right. So now that we have written the general rate law, what we're going to do is determine the exponents. So again, M and N, okay, are they going to be 0, 1, or 2? So we are going to use the data up here to figure out what it is. And this is how I'd like you to write it out. So we're going to look at a series of experiments and compare them and see how did the rate change when you did something to them. So we are going to look at A. How does A affect the rate of the reaction? So what we want is B2 here to stay the same. So if I look at experiment 1 and experiment 2, A is going up by a factor of 2, so it's doubling, and B is staying the same. So that means whatever I'm doing to A is going to affect the rate. Okay, so I'm going to write down experiment 1 and experiment 2. Okay, I see that A is doubling. So write down A in brackets, and you could write down double. Okay, so I doubled A, and then you're keeping B constant. So write down B is constant. And then what is happening to the rate? Well, the rate is constant. So if the rate is constant, what is M going to be? And M is according to A. So how is A affecting the rate? Well, M has to be a zero order reaction because no matter, even though I doubled the concentration of A, my rate stayed the same. Okay. So now what about B? How does B affect the rate? Well, I need 2 experiments where B is changing, but A stays the same. So I'm going to be looking at experiment 1 and 3. And I want you to write this out when you're doing your work. So B is doubling. Okay, what's happening to the rate? Well, it went from 3 to 6. So I'm multiplying it by a factor of 2. So write down B doubles. A is constant. And then what you could say is rate times 2 is what you see happening to the rate. So N, which is what B2 is, has to be a first order reaction because I doubled the B, the rate went up by a factor of 2, so that is a first order reaction. Okay, so that is the second part of the problem. Okay, I found zero order and first order. Zero order according to A, first order according to B2. So the last thing you're going to have to do is find the letter K. Okay, so that's the rate constant. This is the same for any chemical reaction. For this, I always want you to use the data from experiment 1. And that is because some of this data is made up, and so some of them haven't been really checked thoroughly. And the other thing we're going to focus on is what are the units of K. So I'm going to take this general rate law expression and plug in the data and see what K comes out to be mathematically. Okay, so I'm going to say for experiment 1, I have 3 molar per second is my rate. My K is what I'm trying to find, so you can make that your X if you like to do it that way. My A is 1 molar, and it's brought to the 0 power. B is 1 molar, and it's brought to the 1st power. Okay, so anything brought to the 0 power, you could just cancel it out. And so what I have here is essentially 3 divided by 1, so K is going to be mathematically equal to 3. That's never the hard part. The hard part is always going to be finding the units of K, finding the units of K. So what I'm going to do is I'm going to use the units here and then solve for K that way. Okay, so I'm going to have molarity over seconds is over on the left. The 0 order cancels it out, and so I'm left with K times molarity to the 1st power, molarity to the 1st power. So I need to get X by itself. So what do I have to do? I have to divide both sides by molarity. So what are my units of X? It's going to be 1 over seconds. So this is 1 over seconds is my final answer. Okay. All right, now maybe it might be easier to understand if you have actual real data, maybe not a real chemical formula yet, but real data. So let's do this problem here, and that might make it make a little bit more sense when the numbers are a little easier to see. So again, if you want to make it a table like this, you'd see experiment 1 and experiment 2. So writing a general rate law, again, that's the easiest part, right? Rate is equal to K. And then you're going to write however many reactants in brackets. So A2B6, you must write the actual chemical equation and bring it to the power of M. Okay. Then I need to figure out what the exponent is. So is the exponent going to be 0? Is it 1 or 2? So I have to see what is happening to the concentration and what happens to the rate. And this is where, again, you're going to have to use your calculators because sometimes the numbers are not going to be that nice to look at. And I would suggest you could easily take 2 experiments and divide one by the other to see what is happening to the numbers. So again, if you can't see what is happening in terms of concentration, take the bigger number over the smaller number. So I'm going to take 0.112 and divide it by 0.056. And I'm going to see that I get approximately 2 when I divide those 2 numbers. I then take a look at the rate for experiment 2 over experiment 1. So I'm going to take 1.38 times 10 to the 3rd divided by 3.45 times 10 to the 2nd. And I get approximately, and again, it's never going to be a perfect number, approximately 4. So what is happening to the concentration of A2B6? It is doubling. Okay. What is happening to the rate? It is going up by a factor of 4. Okay. So for this type of problem, you can just verbally write out your answer, or you could show me the math calculation so that I could see where you got your numbers from. But because this is doubling and the rate's going up by a factor of 4, I know that M must be equal to 2. It must be a second order reaction. Okay, and finally, I'm going to use experiment 1 to find my K. So I'm going to take 3.45 times 10 to the 2nd is equal to K times 0.056 molarity to the power of 2, So I'm going to take this number and divide it by 0.056 squared. So the math is never the hard part with these problems. So you get a pretty big number, 1.1 times 10 to the 5th. So again, you will always be asked to find the units here. And so I always like to write out the units and do it that way. Some of you are going to find it go a little faster as you do more of these, but as long as you can show your work. So I have K times molarity squared, and I have molarity over seconds over here. So I have to divide both sides by molarity squared, to cancel it out and have K left over. So if I have molarity squared on the bottom and molarity on the top, molarity cancels out, but realize that becomes a 1 on the top. So my unit here is going to be 1 over molarity seconds, 1 over molarity seconds.